Here we'll give a brief introduction to separations using membranes. And the idea is that we feed a mixture in, and the chemical potential, say here, feed is higher than the chemical potential in the permeate. So this could be because of pressure, because of concentration differences. And then the depleted feed, the retentate, depleted in the component that we want to permeate. Now, there's lots of reasons why we might want to use a membrane. One of the big ones is for energy savings. This is because if we don't have a phase change, which for some of the separations by membranes, or in most of the separations we don't have a phase change, then we don't have to put in that heat of vaporization and then have to condense the phase back. We also can run this continuously. An additional advantage is that we can run at low temperature. So if we're not evaporating, not having the heat to a high enough temperature to get a significant rate of evaporation, then the materials that are temperature sensitive are not going to be damaged. Also, if we have a mixture that possesses an azeotrope in distillation that makes separation difficult, this is not going to be important for membrane separations because we're using a different mechanism for separation. Likewise, if we have a mixture whose boiling points for two of the components are close together, so we take a very large distillation tower, for example, again, membranes using a different mechanism can separate such a mixture. So let's look at the types of separations that we might carry out using membranes. So for example, on the left I'm showing going from high concentration to low concentration. I have a mixture on one side, and then on the permeate side I have preferentially the smaller molecule that permeates. So this, for example, is the type we would use for gas phase membrane separation. For example, if we want to separate CO2 methane for natural gas purification, then the separation can be based on size of the molecule. It can also be based on having one of the components adsorb more strongly, so based on either adsorption or absorption, and more than one of these can be operative. Now, for all these separations, there are several things that are important for using membranes. One is we want high permeance, and permeance is the flux through the membrane divided by the pressure difference, the driving force. So moles per centimeter squared per second, that's flux, and then pressure is bars. So that's the units. Now, permeance is also related to permeability. So permeability is a more innate property of the material, and as we have a thinner membrane for the same material, we're going to have a higher permeance. So to have high permeance is one, it's a function of the membrane and its thickness. It's also a function of what's the driving force. For example, in the gas phase separation, I showed what's the pressure on the feed side, and a function of temperature. As temperature goes up, typically diffusion rates go up, but solubilities, adsorption go down, so permeance can go either way with temperature. Second important aspect of membranes, and a critical aspect, is selectivity. In other words, how well do we preferentially permeate one of the molecules through the membrane? So for this separation, selectivity would be defined as the permeance of CO2, that's what we'd like to preferentially permeate, over the permeance of methane. You also will see another term, that's another way of expressing selectivity, and that's a separation factor, and that's related to mole fraction. So mole fraction of CO2 on the permeate side over the mole fraction of CO2 on the feed side, and then divided by mole fraction of methane on the permeate side, mole fraction of methane on the feed side. So we can get a higher selectivity or separation factor if we have a better membrane. We get a lower selectivity if we have concentration polarization affecting the membrane. So for example, if this is the feed side of the membrane and we're permeating water but not a solute, such as reverse osmosis, then the water concentration can be reduced at the feed side of the membrane, and the solute concentration can be increased because water is permeating, not the solute. Now the solute has to diffuse away from the surface, but the lower concentration of water means a lower driving force, and this can be compensated by creating good mixing near the surface, by having a high flow rate across the surface to minimize the boundary layer. So in addition to permeance and selectivity, the other important property of a membrane is lifetime. If they don't last very long, they're not going to be economical to use. So lifetime can be decreased because of degradation. For example, a polymer who degrades with time, or because of fouling where material builds up that plugs pores of a membrane or blocks the surface of a membrane. So membranes can be very economical. They're used on a large scale for things like reverse osmosis, and they're used increasingly for gas separation and pervaporation.